Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will continue to unpack potential and potential difference. Alright, so now let's apply what we learned in the last video about sort of what is happening to the charges when they hit the resistor, and we're going to make it a little more quantitative. So consider a simple circuit again. This is just the resistor with a current that flows from one point out of the battery through the resistor and then back into and then through the battery. Note that first, because the resistance of the resistor itself, the green R, is much, much bigger than the resistance of the wires, we're assuming the resistance of the wires is 0. We actually have been doing this the whole time around, but it's important to recognize what would happen if you took the resistor out, which is that suddenly the resistance of the wires is the only resistance that matters, and so you'd actually get a pretty big current. This is called shorting the circuit. So we just connected a wire from this point to this point, we would short the circuit and get a pretty big current, as much as the battery and the materials could sustain. So what is actually happening? So without formally defining exactly what potential is here, rather than just potential difference, it's very, very useful to understand what potential is as opposed to potential difference, or have a concept of it. So we don't need the formal definition to do this. And the general idea is that potential is a function of position that keeps track of the energy per unit charge of the charges in the circuit. And in that way, it's a lot like height for gravitational potential energy rather than electric potential energy. So the potential is like a particular elevation or a particular height. In a circuit, if this is sort of our battery, we can model what is happening with the potential as sort of like a little hill. So in the hill, in this sort of model, you can imagine like an escalator or something. The charges are given energy at the battery, right? That's your EMF. And they're sort of given energy, given energy, given energy. It's like being given height. In the same way, they're given potential. They sort of climb the potential ladder at the battery. That's what the battery does. Now they have a lot of energy. Now, as they go through the circuit, they then lose energy, and in fact, they lose the majority of their energy in this kind of a circuit, the vast majority, and we're assuming basically all of it, at the resistor. And at the resistor, they deliver that energy to the resistor, and so the potential is understood as like, it's kind of like the height along here. It has the same relationship. So if you imagine this as gravitational potential energy, it's like these little charges are being given gravitational potential energy, and then they're losing it as they go sort of down the hill and deliver it to, I don't know, imagine sort of a water wheel right here, and the water sort of moving past it. And the difference between potential and potential difference is that potential is a particular elevation at any point, and potential difference is the gap in the elevation. So the EMF is the gap between where the charges are at the start and where the charges end up. And it's the amount of energy per unit charge given to every charge. All right? It's the amount of energy per unit charge given to every coulomb there. And then they lose that exact same amount of energy when they go through the resistor. As a result, sort of decrease in elevation, or what we call potential. So in a circuit, you can really think of potential as like H in the gravitational potential energy formula, and potential difference is like a gap in elevation. And this explains why in our simple circuit, sort of the EMF is exactly equal to the potential difference across the resistor. They are not identical concepts, but they're identical values here because, fundamentally, of the conservation of energy. If the charges are given this much energy, right, the EMF worth of energy, then they will lose exactly that same amount of energy at the resistor. And we can plot this by considering sort of the potential itself at every point around the circuit. If I start out right here at sort of position 1, and then I'm going. I'm at the same potential. And then in the battery, I climb in potential. I gain energy, going. And then I stay flat for a little while. I'm in the wire itself. And then I lose energy down our slope here through the resistor. And then I'm at that same elevation again. And you can see why the sort of potential difference and the EMF have to be the same. It's also worth pointing out that the potential all along this area of the wire and all along this area of the wire is the same, as long as we assume that the effective resistance of the wires is 0, okay? If you wanted to sort of map out the potential, you could actually give it values, just like you could height. And just like the gap in height is what really matters in gravitational potential energy, it's the gap in potential that matters in potential difference, not the actual potential. So here's one way of outlining this circuit, right? We started at sort of what we'll call 0 volts, and then in the battery we gained potential, 1.5, 3 volts, and then we stayed at that potential, and then we dropped over the course of the resistor, right? In potential, we went from 3 to 2 to 1 to 0, and then we stayed at 0 volts again for sort of that second half of our simple circuit. So why do we focus on potential difference and not potential? As I mentioned, it's because that potential is not absolute. It's relative. Just like in gravitational potential energy, we can set H equals 0 anywhere. In a circuit, we can set V equals 0 anywhere we want. So the following circuits are all exactly the same. Although the potentials given are different, the potential differences are all exactly the same. So this is the same circuit that we just looked at. Well, you could imagine setting, just like you would set H equals 0 somewhere, you can set this particular point to be 10 volts, or consider it to be 10 volts. So if this is 10 volts, then you'll get the same potential difference as the EMF in number 2, and then the same potential difference across the resistor from 13 volts to 10 volts. That's exactly 13 volts minus 10 volts is 3, just like in our first example. Notice that this is true for negative values of potential too. So just like height, you can use a negative value of the potential anywhere you want. So if we have a negative 10 volt potential right here, then across that gap, across the EMF, you would have a negative 7 volt potential because it's 3 volts higher. Notice that this has not been written very well. That should be negative 8.5 volts. And then as you come around, notice that you drop in potential going this way. Notice that that's a drop because these are negative values. So don't be thrown off by the fact that negative 7 is a higher potential than negative 10 volts, even though 10 is the higher number. That's just a negative number kind of thing.